Hi, I'm Dave Waddell. I work with the King County Hazardous Waste Management Program, and I work as an environmental investigator. I suppose one of my claims to fame is that I was the person who created and ran the Rehab the Lab school chemical cleanout program for several years for King County. The training video that you're watching today is going to focus on four major topics. We're going to focus on high hazard chemicals, like these cans of sodium I've got standing next to me here. We're going to focus on how to properly store your chemicals to make sure that you don't have incompatible chemicals stored next to each other. We'll talk about spill management and how to respond to a spill and how to determine whether it's a spill you can respond to or it's a spill that you should call somebody in to respond to. And lastly, we'll talk about hazardous waste disposal. So if you find stuff like this really old sodium I'm leaning against, you'll know how to get rid of it. And for your more routine waste streams like your aqueous metal solutions or your alcohols, you'll have an idea of how to properly dispose of those so you're doing what you need to under the law and also doing it as inexpensively as possible. And in this section we'll be talking about high hazard chemicals. Quite often where we'll find them is in a flammable cabinet just like this one, which you find in many of the schools. What we're going to be looking for is whether we'll find something in here that could potentially explode just by mishandling it, and how to identify those compounds, what some of them are, and why you would possibly even have them in your school. So when we're talking about hazardous chemicals in schools, there are hazardous chemicals that would count as hazardous waste, and then there's highly hazardous chemicals, which actually pose an imminent threat of explosions or reactions or other things that could create a very hazardous situation in the school. So that's what I want to focus on in this discussion. So first off, what do we consider high risk? There's four major areas that I focus on. Things that could potentially explode, things that if you literally spit on it or breathed on it could burst into flames, carcinogens, teratogens, neurotoxins, chemicals that can create long-term health hazards, especially to children, students in the schools. And then poisons that can create a toxic reaction just by touching them or breathing them in. So where do we find these kind of things? Who would imagine these would be in schools? Well, we find them pretty much in the science laboratories, but also we find them in the art departments, sometimes in the maintenance shops, and they could be tucked away in custodians' closets and other areas where old chemicals have been hidden. Now, these things are not typically things that are currently being bought. These are chemicals that have been sitting around for a long time, potentially have degraded, and for some of the things, like the potentially explosive chemicals, it may not be that they were explosive to begin with, but now that they've sat for 20, 30, 40 years in your school, they may have degraded to the point where they could become shock-sensitive explosives. And I'll expand on what I mean by that in a second. So what are some of the explosive chemicals we can find in schools? Well, first off, you need to realize that these things are more common than you may expect. In King County, Washington, and the Seattle area, 44% of the schools that we visited, of the high schools we visited, had potentially explosive chemicals in them. These included things like picric acid, ethyl ether, tetrahydrofuran, elemental potassium, collodion, cyclohexene, acetaldehyde. Some are pretty obscure, some were a little more common. Let's go ahead and focus on some of those. So we'll start by talking about picric acid, which is also, its chemical name is trinitrophenol. Now, trinitrophenol is essentially TNP. Trinitrotoluene is TNT, so these two are very similar compounds. And the dinitro and trinitro organic compounds all have this risk of being explosive. If you see something like picric acid, trinitrophenol, or something that's labeled picric acid, could also be labeled Bouin's fluid, B-O-U-I-N, apostrophe S. These are essentially bomb squad materials, especially if they have a metal cap. The picric acid can react with the metal in the cap and form shock-sensitive explosives. These are things where just twisting the cap can be enough to detonate the compound. 1 pound of picric acid is equivalent of 6 or 7 sticks of dynamite. It's enough to move concrete walls back. And obviously, if you're in a classroom or a stockroom where there's a lot of other bottles of chemicals, the shock wave is going to be enough to break every glass bottle in the room, which has a secondary possibility of creating a chemical reaction that would carry the explosion into a fire or other types of problems. So another type of possibly explosive chemical we find are the peroxidizable solvents. And by far the most common of these is ethyl ether. Ethyl ether is a highly flammable chemical. It's used as a starter fluid in engines. It's also used in the biology lab to put fruit flies to sleep. It's not explosive in itself until it is opened. Once the solvent comes in contact with air, there's a possibility of peroxide crystals starting to form. And typically where those things will form is in the threads of the cap, because that's where the air can get in and this volatile solvent can get out, and that where the two come in contact, these crystals can form. These crystals are equivalent to those little snappers that you can throw on the ground and they snap for the 4th of July. The problem is you've got these little snappers that can detonate, again, by just twisting the cap on a can or a bottle that is full of a highly flammable liquid with a lot of vapor. If you put a flammable liquid like this and its vapor and you ignite it very quickly in a closed container, that's pretty much the definition of a bomb. Other types of peroxidizable solvents include tetrahydrofuran, ethyl ether, isopropyl ether. So these are things that do form these crystals. Now let's talk a minute about crystals in bottles. Do you just always assume that if you see a crystal on a bottle that it's going to be explosive? No. Crystals form very readily on acid containers, and in the photo you can see these blue caps with crystals around them. It's hydrochloric acid. These are probably ammonium chloride crystals that have formed from reaction with another compound. Not even particularly toxic. But if you see them on a solvent bottle or on a picric acid bottle, brown glass bottle, that type of thing with a crystal on it, that's a very risky situation, and you should definitely treat that container with great care. Anytime you see a brown glass bottle with crystals around the cap, don't open it. Bring in your hazardous materials specialist from the local fire department, possibly the bomb squad, or maybe even a contractor to come and take a look at those. You can't just assume that they're safe just because it's a bottle that's been sitting in your lab for a long time. So of the peroxidizable solvents, the one that we found that's the scariest is isopropyl ether. It's very rare to find it in schools, but if you do find it, you need to consider this thing to be a bomb as soon as you see it. It forms peroxide crystals very quickly. The rule of thumb is once you've opened the bottle, you have 1 month to use it up before it started the peroxide forming process. In the bottle that we're showing in the picture here, crystals were in the bottom. Enough pressure had built up in the bottle to cause gases to form, and it expanded to where when they set the bottle down, the bottle actually shattered on the table. Fortunately, they were able to move it outside, the crystals outside, and get away from them before they auto-detonated and exploded. Obviously, this is a very hazardous compound, and if it's in your school and you see it, you need to assume that it's explosive. Another peroxide former that is unlike the others is metallic potassium. And this is actually a chemical we find pretty often in science laboratories. The pure element of potassium is highly water reactive, and it can form peroxide crystals over time. In this case, it's not so much that there's a flammable solvent, it's that the peroxide is formed when potassium reacts with the air. So there's actually a color code of sorts that goes with potassium metal. When it's brand new and it's just gotten shipped to you, it'll be silver. Somewhat shiny, maybe a little dull. Once the potassium's been pulled out of the container and has been used, if you've chipped off a little piece to show that it is water reactive, it's going to react with the moisture in the air and it will start the process of oxidizing. So potassium metal is different than the solvents in that it's not a flammable liquid, and the peroxidation process is the same in that it reacts with the air, but it also reacts with the moisture in the air and starts that process a little more quickly. You can actually tell what stage of peroxidation it is in the process on potassium by looking at the color of the stick that you have under oil in the jar. If it's silver, it's brand new. You don't need to worry about it aside from the fact that it could burst into flames if it got wet, but that's probably why you bought it in the first place. When you start seeing it turn white, it's gone from pure potassium to potassium hydroxide. At this point, it's corrosive, though it's not explosive. This is fairly common. Those crystals can be scraped off and the potassium can continue to be used. It's when it starts turning other colors that we start worrying about it. The next stage from white is to become yellow, and it starts getting into orange. At this point, it's forming a superoxide. This is an unstable oxygen-to-oxygen double bond that, when it's broken, can release a lot of energy. At this point, it's still water reactive, it's still corrosive, but when you put the little piece in water, it may not just burst into flames, it may actually detonate. So you're getting sort of a chain reaction type of thing that builds up. When it starts turning red and purple, now that chain reaction can be initiated just by trying to cut the piece of metal that you've got out to try to use for your demonstration. At that point, it's a high explosive, essentially, and needs to be disposed of as an explosive rather than just a water reactive material. Now, why would a school have potassium metal in their classroom? Why would they still be buying it? Well, it's a great demonstration material. And the most common way it's used is to demonstrate the water reactivity of the earth metals. If you look on the first column of the periodic chart, you'll see hydrogen, which is kind of an odd duck in that group since it's a flammable gas. But after that, you've got lithium, then sodium, then potassium. And many science teachers will do a demonstration of a small piece of lithium in water, then a small piece of sodium in water, then a small piece of potassium in water. And what you'll see is the lithium sort of dances around on the top of the water, fizzes, like putting a fizzy in there. The sodium will do the same thing, only it'll generate enough heat to actually become a molten ball and go shooting around the top of the beaker full of water. The potassium will do more than that. It'll actually burst into flames and go bouncing around and burn up very quickly. So by showing that, they can show, A, what water reactivity is, and that you have increasing reaction as you go down in the periodic table. So how can we keep this really great demonstration viable for students so they can actually experience a visual, auditory nature of chemistry, but not have something that's going to blow up in your lab if you mishandle it? My recommendation is that you continue using the lithium because it's not particularly hazardous. Continue using the sodium, but buy small chips, and Flynn Scientific and other chemical companies will provide these small chips. So you just use the tweezers, you can drop them in. They sell you about 5 chips at a time, so you're not buying a pound of this stuff and trying to cut small pieces off. And then discontinue the use of the potassium. There are videos available that can show what the potassium reaction looks like. So show the lithium, show the sodium, then shift to a video and you can show the potassium. And while you're at it, you can also show rubidium and cesium, which you would be crazy to have in your school because they're so explosive in water. But the demos, some other crazy person has shown them on the videos, and you can show them to actually show the whole series. It's a good way of doing hands-on chemistry, but not creating a high hazard risk in your classroom. So we've talked about these potentially explosive compounds. Let's talk about some of the water and air reactives that you may have in your school that are also a high hazard compound and create some additional risks. One of the ones we see fairly often is elemental phosphorus. This is a highly flammable solid, and it comes in 3 forms. It can either be red, yellow, or white. The red phosphorus, which is by far the most common, is not air reactive. It's very poisonous. It actually used to be the red ingredient at the tip of matches, which is why matches are still red even though they don't use phosphorus anymore. And the reason they don't use phosphorus is because kids used to suck on the matches and be poisoned and die. But as you know, with the match, once you've got it ignited, the red material burns very hot, so it's a highly flammable solid. White and yellow phosphorus are pyrophoric, which means they spontaneously ignite in the presence of oxygen or in air. They're generally stored underwater. And in the photo you see here of the ball canning jar with the white phosphorus in it, note the rust on the cap. What's happened is that the phosphorus that's in there, and this is about 1/2 pound of phosphorus, which is a lot of white phosphorus, has reacted with the water and created a mild acidic solution, which has reacted with the metal cap and rusted it. So you've got a material that reacts with air, can spontaneously ignite, is stored in this case in a middle school underwater, but it's got an open lid with the rust holes in it. So in a nice warm room, the water level starts lowering as the water evaporates. And if you look, we've got about 2 millimeters to go before the top of those phosphorus sticks start getting exposed to the air in that container. At that point, they spontaneously ignite, generate a lot of steam, probably popping either the lid off the jar or cracking the jar itself, at which point sticks of phosphorus go falling out of the jar onto the wooden counter in the stockroom full of chemicals. They get dry, they spontaneously ignite. Phosphorus burns really, really hot and will very quickly burn a hole right on down through the wooden cupboard and set the entire lab on fire. Sprinklers are not enough to put out white phosphorus once it gets burning, so this is a fire that's not going to go out easily. Not only that, but all of the phosphorus metals are highly poisonous, so any smoke that comes off of these things is also highly toxic. This is one of those chemicals that we say has a risk that exceeds its educational utility. I don't know what you're doing with the phosphorus, but just because something can spontaneously ignite, it's not necessarily great chemistry. It's a good woohoo type of thing for the kids, but I'm not sure they're getting as much out of it as the risk is posed by this compound by having it around. We've already talked about metallic sodium and lithium and potassium, which are water reactives. Those are about the only truly water reactive compounds that we would recommend even considering having in the lab. Anything else, the risk posed by having these things is really not as good as the benefits from teaching with them. So if you're going to have a water reactive, have the lithium, small pieces of sodium, and why don't we just call it there. Now, the other ones that we worry about quite a bit are the developmental and neurological toxins. And by far the one we're most concerned about here is elemental mercury. We still see mercury in schools. Mercury in the state of Washington is now banned from being in any school. This law came into effect on January 1st of 2006. So you can't have any bulk mercury, you can't have any mercury compounds, no mercury novelty items, the little mercury mazes or the mercury necklaces. The tennis shoes with the mercury switches in the back of them are banned from schools. And mercury devices, the law does allow one mercury barometer to be in a school. Our experience is that almost none of these mercury barometers are actually actively being used by teachers, and they do have a lot of mercury in them. So we recommend that your school not have mercury barometers in them. And mercury thermometers are still common, but it's very easily substituted for. There are digital thermometers now that are more accurate than the mercury thermometers. For routine use, the alcohol thermometers work perfectly fine. And if you do have a spill, you're not looking at thousands of dollars to try to clean it up like you would be with an elemental mercury spill from a mercury thermometer. Okay, so what other neurotoxins do we find in schools? Well, several neurotoxic compounds are commonly used. One of the most common ones are the hexavalent chromium compounds. One of the rare ones, thank goodness, are the arsenic compounds. We still periodically will find some arsenic in schools, but I think most schools have recognized that arsenic is highly toxic and gotten it out of there. The hexavalent chromium compounds are the chromates and the dichromates, and we still see them fairly often. In a high-level teaching environment, advanced placement chemistry, something along those lines, college-level chemistry, the dichromates, in particular potassium dichromate, do have a place in that venue. We recommend that they only be purchased in a solution, pre-diluted, and that way you don't need to run the risk of people breathing in heavy metal fumes and heavy metal dust from these compounds. They're also much less reactive. All of the dichromates and chromates are powerful oxidizers, and in contact with any organic material, there's a great risk of them bursting into flames. So now you have something on fire that's also generating carcinogenic smoke, not something we recommend. The other place where we see the hexavalent chromium compounds, the dichromates in particular, is ammonium dichromate being used in the famous volcano demonstration, where essentially it's set on fire, and it does make great sparks and flaming red glow and the whole bit that makes a very active and exciting volcano. The problem is you're generating carcinogenic smoke coming out of it, and you're creating a hazardous waste that's very difficult to clean up. So this may be one that, even though it's a really great looking demo, the risks again may exceed its educational rewards. Other things we see that are known carcinogens in schools, periodically we'll still find old bottles of benzene. That's very rare, and I don't know anybody that I've worked with who's using it in school. This is just a good one to get rid of it, but highly flammable, a known carcinogen. Asbestos we still find, and typically that's used in triangle heating pads that they put under the over top of the Bunsen burner. There are non-asbestos alternatives for that, so those are good ones to get rid of. Formaldehyde we still find fairly often, and generally where we're finding it now is in the actual tissues of the preserved specimens. So the sheep brains and the fetal pigs and those type of things. The holding solution should be something other than a formalin or formaldehyde solution. There's Carosafe and Flynn-Safe and Ward-Safe and these other ones, which are a propane diol or propylene glycol solution. If you don't know what the holding solution, the liquid that's holding those tissues are, if you don't know what the holding solution is that's holding those preserved specimens, I would assume that it's formaldehyde and get rid of that stuff. Formaldehyde is a known inhalation toxin, creates a horrible allergic reaction over time and exposure. A lot of old biology teachers can't be around permanent pressed clothing, pressed wood, new carpeting. All of these things have formaldehyde in them and can create a real serious reaction, asthma symptoms, that type of thing. All of the nickel compounds are known carcinogens. All of the cadmium compounds are known carcinogens. So these are ones where you definitely, if you're going to be using it, they need to be diluted. You need to make sure people are using good personal hygiene, washing their hands after class, wearing gloves when they're in contact with these materials. Teratogens are a group of compounds that people are not as familiar with. It's a term that people have not heard as often. These are essentially developmental toxins. These are things that interfere with the development of the embryo, and they can carry on through multiple generations. One of the teratogens we find commonly in schools is paradichlorobenzene, and the most common place we find this is in the urinal in every boy's bathroom in schools. Occasionally we'll find the blocks hanging on walls in the girls' bathroom also. Basically what it does is it interferes with your sense of smell, kills off your scent organs, so you can't smell anything besides it. And you notice you don't even smell it after a while because essentially it deadens your sense of smell. It does nothing to sterilize anything. It's not a disinfectant. It's just a fragrance. It's just a highly toxic, birth defect causing fragrance. So this is one we recommend just be eliminated from schools. There's no real place for it. I've already talked about formaldehyde. It's not only a carcinogen, it's also a teratogen. Xylene and toluene are also known teratogens, common constituent in paint solvents and flammable paints. Very volatile, inhalation hazards, that type of thing. The skin contact hazards are another one that we find a lot of, and this is because acids are very common in schools. In the photo here, you see a brown box with a little red circle in it. That red circle is a cap to a nitric acid bottle. Nitric acid is a very highly corrosive oxidizing acid, and what it will do is eat through its cap in about 7 to 10 years. So if you've got a nice new bottle of nitric acid and you leave it sitting there, in 10 years your nice new bottle of nitric acid is now working its way out of its cap, evaporating and spreading through your entire laboratory. If you find yourself coughing every time you open your acid cabinet, if you find yourself catching colds that never seem to go away, it may be because you have a leaking bottle of acid in your lab. The acid that we're most concerned about in schools is hydrofluoric acid. Hydrofluoric acid should always be in a plastic bottle because it dissolves silica. So it dissolves glass. If you transfer hydrofluoric acid, which is a clear liquid, into a glass bottle, you'll have a puddle of clear liquid on whatever counter or shelf it was on. It looks just like water. However, if you touch it with your bare hand, there's a very good chance you'll lose any fingers that came in contact with it in a very short order. A good example of just how deadly this material is happened in 1995 when a technician in Australia spilled about 200 milliliters, a quarter of a quart of hydrofluoric acid on both their thighs while they were working. They immediately got underneath a safety shower, washed their legs for 15 minutes. They didn't take their pants off, though. And the problem was they also didn't have calcium gluconate gel, which is the only thing that will neutralize hydrofluoric acid and stop its toxic effects from happening. So they had 9% of the person's body was burned. Within a week, they amputated the right leg because the hydrofluoric acid penetrated and started dissolving the bones of their right leg. 8 days later, the person was dead. One of the scary parts about it is that it's an anesthetic. So unlike other acids like nitric acid, which would burn like crazy if you got them in the palm of your hand, a small puddle of this in the palm of your hand will disappear in a few minutes. It's because it passes right through your skin like it wasn't even there. It doesn't burn. It's an anesthetic. So you don't know. Your hand could be wet and you wouldn't even know that it was wet, let alone that you had an acid on it. Once it gets in there, it immediately gets into your bloodstream, forms a fluoride ion, which is very toxic, and starts disintegrating your bone to form calcium fluoride. So it's the sodium fluoride from the salt in your blood and the calcium fluoride from your bones. So it's disrupting your blood flow It's disrupting your bone formation. At that point, it's described as a deep gnawing ache, and it lasts for months before it goes away. Just about drives people to insanity. I've met one person who's been exposed to it. It was 6 months before they were able to use their leg properly again. And this was a very small exposure. So essentially the leg stopped working, but it was horrible pain. They were on morphine derivatives for months in order to cope with it. So this is clearly one of those chemicals where its risk greatly exceeds its utility. And what's particularly scary to me about it is the most common place where we find hydrofluoric acid in schools is in the art program. Because it dissolves glass, it's used for glass etching. So in a chemistry lab, they may be wearing splash aprons, lab coats, chemically resistant gloves, goggles. They may be using it in a fume hood, which pulls all of the vapors away. In an art program, they typically don't have any of these things. Maybe latex gloves, which provide very little resistance to hydrofluoric acid. So these are ones that we really focus on in the art classroom as much as in the science classroom. Let's talk about toxic inhalation hazards. These are actually materials that we find fairly regularly in schools still. And these are compounds where if the container is broken or is opened, they're either liquids or gases at room temperature and are going to start spreading through the room. And breathing them in can create an inhalation hazard to you. One of the most common ones we find is bromine. Bromine liquid, bromine solutions. And when you breathe in bromine vapors, it forms hydrobromic acid in your lungs. Once your lung tissue is acid burned, it doesn't regenerate very well. The alveoli tend not to recover. And so this is a compound where, unless it's in solution, being used in a fume hood, the risks are very great. One of the scary parts is that it also eats through its cap, similar to nitric acid. So if you just leave it stored, that doesn't mean you're not going to get exposed to it. And it's often shipped in blown glass ampules, like the one shown in the center photo here, which are highly fragile. The idea is that you would etch this with a triangle file and break the ampule open under a known volume of water to form a known concentration. In my experience, though, almost no one does this as soon as the thing arrives at their site. They pull it out, put it on the shelf, completely forget about it. Because they're small, they tend to tip over, and then somebody sets a bottle on top of it and closes the door. The next time they open the door, this beautiful magenta cloud comes out, at which point they go and suck it right down into their lungs and start coughing their lungs right back out, or something very similar to it. We've actually found chlorine gas cylinders in at least 3 or 4 of the schools we've visited, which were planned to be bubbled underwater to form a known concentration. Please, if you absolutely have to have chlorine water, buy it pre-diluted. Let somebody else take the risk of having an escaping chlorine gas entering their school. These are all compounds that just pose a risk that we think should not be faced by students or by teachers. And frankly, most of these things, the person most at risk is not the kid in the class, because the teachers are watching out for their health. It's the teachers who are preparing diluted solutions from these highly concentrated compounds. And we don't blame teachers for buying these things. Most of these things were there before they were even born. A lot of these compounds date back to the 1950s and 60s when they were first purchased. And once people realized how hazardous they were, they just left them sitting on the shelf. So the new teachers have come and inherited these things, and quite often without an awareness of the risk that they're facing. And that concludes my talk on the high hazard chemicals. If you have questions about this information and these materials, feel free to contact me. I can be reached, Dave Waddell. I'm with the King County Hazardous Waste Management Program. You can email me at dave.waddell, that's Waddell, @kingcounty.gov.